Hey, let's go over question one from last year's 2019 AP Calculus exam, the AB version. So you'll notice question one here says that a graphing calculator is required. That was true last year, right? That's true standard for the typical test. That's not going to be true for you. A graphing calculator will not be required. It wouldn't hurt you to have one nearby, but it's not going to be required. So just kind of keep that in mind as we go over this. Now, you might be saying, well, why are we going over this then? Well, because the concepts in here are definitely going to be tested on your test. They just might be asked in a slightly different way, and we'll go over that as we do the question. All right, so here we go. It says fish enter a lake at the rate modeled by the function e, given by this function right here. Fish leave the lake at a rate modeled by the function L, given by that function there. It says both E of t and L of t are measured in fish per hour. That gives you a good idea of what's going on here. And t is measured in hours since midnight, which they're saying, hey, that's going to be t equals 0. So midnight's going to be t equals 0. All right, so this is standard issue stuff here, guys. You have a question where there's an incoming rate and an outgoing rate. You know, there's a really good chance you're going to have a question where that is the case, okay? Sometimes it's fish coming in, fish going out. Sometimes it's water coming in, water going out. Sometimes it's sand going onto a beach, then sand leaving the beach. Sometimes it's people entering a line and then people leaving a line. It's all the same thing. You have a rate of something coming in and a rate of something going out. All right, so you should be pretty comfortable with doing these questions. So let's get after it. So I make a note of my two rate functions and their units, right? And I go to the first question. How many fish enter the lake over the 5-hour period from midnight t equals 0 to t equals 5? Give your answer to the nearest whole number. All right, so if I want to know how many fish enter the lake, then I have to integrate the enter rate, right? So you shouldn't even be looking at L of t for this question. It should make sense that out. If I want to know how many come in from 0 to 5, then let me integrate 0 to 5, from 0 to 5 of E of t, which you could just write E of t, but I'm going to write it out, of E of t dt, right? If I integrate the rate at which they come in, I get the net change in, how many came in, basically over that time period. So now this was on the calculator portion of the exam. So last year, all you were expected to do was set it up like this and then do it in your calculator. So have your calculator do that integral. And if you did that, you would get 153.457. And in this particular case, they actually ask you to round your answer to the nearest whole number. So that would be 153 what? 153 what? What would the unit be? A lot of times they tell you to clarify the unit. Here they did not, but you should know what the unit is. It would be fish, right? Now, why is that? Why does that make sense? Well, because when you integrate the rate function, remember, this function, this y unit, is measured in fish per year, right? I'm sorry, fish per hour. Fish per hour. And you're integrating with respect to t. So you're integrating with respect to hours. So to get the unit for the integral, right, you can always just multiply the y unit and the x unit. And when you do that, you end up just getting fish. That's a good little, I wouldn't call it a trick, but a good way to figure out, well, what does this integral mean? How do I put this integral in some sort of context? Well, just multiply the y and the x unit, and that's going to be the unit of the integral, which in this case is fish. So that means that's the net amount of fish, the net change in fish from t equals 0 to t equals 5. Okay? So pretty basic stuff there. So now on last year's test, you would have gotten this question. It would have been 2-point question, 1 point for the setup, and 1 point for the answer. So now the question is, could they ask you this exact question this year? And it turns out they could, although it might be annoying, they could ask you this, right? Because you could do this integral without a calculator. That's not always the case with the integrals they give you, but this one it is. So let's practice this. So even though this would not have been expected for last year, we're going to do it just for good practice, okay? All right, so here we go. Integral of the sum, what is that? Integral of the sum is the sum of the integrals. So a function whose derivative is 20, that's going to be 20t, okay? And then now plus, how do I integrate this? Well, I have a constant times a function. So the integral of a constant times a function is going to be the constant times the integral of the function. Now, can you integrate sine of pi over 6t? And the answer is you can, right? It's a composition. Now, when you first were given this, you did it with a u substitution, and you let u equal the innermost function, you let u equal pi over 6t, and you went after it, right? Well, if you remember, we learned a little trick in that when the u was something, right, you could do this trick. Do you remember what u had to be in order for you to do this trick? Hopefully you're answering linear, right? So when your innermost function is linear, then you can do the u substitution, which is kind of like the reverse chain rule. All right. Now, it's not really a reverse chain rule because that doesn't exist, but we call it the reverse chain rule because it's kind of like it, but it's not a rule because it's only true when u is linear. So how would you do it? So you'd view this as sine of stuff. So give me a function whose derivative is sine of stuff. That would be negative cosine of stuff times 1 over the derivative of stuff. And since pi over 6t is stuff, the derivative of that would be pi over 6. And that is basically the reverse chain rule. If I was to take the derivative of what you see right here and simplify, I would get that. If you don't believe me, stop the video and do it. All right, so we were able to get an antiderivative there. So now, fundamental theorem of calculus, we have to evaluate this, right? There's no plus c because it's a definite integral. We have to evaluate this from 0 to 5. So, all right, annoying, but we can do it, especially if we're allowed to use a calculator to do arithmetic. So let's go get them. So just to save a little bit of time, I'm not going to show the actual substitution of the values. I'm going to kind of substitute and do arithmetic at the same time. So 5 times 20, that's going to be 100, all right? And then this would be minus, right? Minus 1 over pi over 6, right? That's just going to be 6 over pi. So 6 over pi, 6 times 15, that's 1630, that's 90. I'm going to get 90 over pi cosine of, put 5 in here now, that would be 5 pi over 6, okay? So that's what I get when I do f of b. Minus, all right, a lot of us just want to, just throw 0 in. There's a 0 there. It all goes away, right? We've been told a bazillion times. That's not always true. 20 times 0 is definitely 0, but then you get minus, right? Same deal, 90 over pi cosine of pi over 6 times 0, cosine of 0. Cosine of 0 is not 0, right? Cosine of 0, unit circle, right? So whoop, whoop, 0 is over here. Cosine's the x value, right? So that's a terrible unit circle, but you get the idea, right? So cosine of 0 would be 1. So that right there would be 1. And listen, I'm not going to sit here and crunch the numbers with you. If this was your test, they may ask for the exact answer, in which case there's not much you're doing here other than writing minus is plus and changing that to a 1. All right, so go get them if that's the case. But you can check it out on your own. If you go ahead and put all of this in your calculator, you're going to get that decimal, okay? So just a little review of doing a linear u sub there because you're going to have to do that. All right, so let's rock and roll. So let's go to the next question. All right, so the next question says, what is the average number of fish that leave the lake per hour? So the average number of fish that leave the lake per hour over the 5-hour period. So now we're talking about the leave function, and then they want the average that leave per hour, so they want the average rate, right? So that function L is a rate function. So essentially, they want the average value of that function. So if you remember, average value of a function over some interval AB is 1 over b minus a integral a to b of f of x dx. Okay, that's how you get the average value of a function. So now the good news for you is this is not on your exam. So they couldn't ask this question in this manner on your test. All right, but for kicks and giggles, we'll do it anyway. So let's do it. So it's going to be 1 over 5 minus 0, integral 0 to 5. I want the average, number of fish that leave the lake per hour. So I want the average leave rate in a sense. So that's going to be the integral of L of t. So that was what? 4 plus 2 to the 0.1 t squared dt. Okay, and that is basically your answer right there. Okay, this is the setup. And again, remember, this was a calculator question. So this question last year was designed for you to just put this in your calculator. And if you put this in your calculator, right, you get that 1/5 out in front, the integral ends up being like 30.295 dot, dot, dot. And then when you crunch that, you end up getting 6.059 dot, dot, dot. And it would be fish per hour, right? You're like, why is it fish per hour? Before it was fish. Well, because you have 1/hours out in front. So the integral would represent fish, but then you have to multiply by 1/hours, right? So that's why it's the average rate there. And that's how you would do that. Now, just a couple of, educational points here. Could you integrate this by hand? So in other words, could they ask you to do this integral on your test? And you might say, well, it'll go for some of the integrals, so that's good news. And then you might even say, this, we know how to integrate these, right? So recall, and this might be one that you put on that little summary sheet, recall that the integral of an exponential, so of like a to the x dx, right? A function whose derivative is a to the x. Turns out it's a to the x divided by ln of a, right? That'll always work. Remember, e to the x is the easiest one in America. Integral of e to the x is just e to the x, and that's because the ln of e is 1. So you're thinking I can apply this with what you just did before, right? Just do that reverse chain rule there, where I can just kind of do, this is 2 to stuff, so the integral will be 2 to stuff, ln 2, and then times 1 over the derivative of stuff, right? Can you do that? Pause the video, answer that question. The answer is no, you cannot, because this is what? This is not linear. So you would not be able to do a fake chain rule or shortcut U sub here. Would not be able. You couldn't integrate this, right? The only way you can do an integral like this is if there was a multiplication of t out in front, like t times. Because when you pick u to be 0.1 t squared, du is going to be something like 0.2 t dt, but you don't have that here. So this could not be done by hand. That's the moral of the story. That's why I wanted to show you that. Again, you will not be asked about average value. All right, it's an easy enough concept, but you're not going to be asked about it. Okay? All right, let's rock and roll. Let's go to C here. It says at what time t between 0 and 8 is the greatest number of fish in the lake? So greatest number. So we're thinking max there. We want a max, right? And then justify your answer. So there's kind of like a couple of ways to go about doing this problem. There's a long way, the short way. I'm going to kind of go through it in methodical way. So here's the deal. If I want the greatest number of fish in the lake, I'm trying to maximize the number of fish in the lake. So do I have a number of fish in the lake function, right? You don't really have that, right? You have E of t, which represents the incoming rate, right? So this is I'll call it the in rate of fish. And then you have L of t, which represents the out rate of fish, right? And how they're coming in, I have no idea. I mean, is they spawning instantaneously or someone's dropping them out of a helicopter? Who knows? But they're coming into the lake, all right? That doesn't matter. And how they're leaving, that's another question. People fishing, what's going on there? Anyway, it's nothing to do with the question. So here we go. So how can I use this to come up with a function that represents the amount of fish in the lake? And believe it or not, we've done these questions before, and this was on one of the tests that you took. So there's kind of like 3 things that you have to consider when you have an incoming outgoing rate problem and you want to know how much is in at any one time. There's 3 things that you have to consider, right? Do you remember? You have to consider how much you start with, how much has come in, and how much is left, right? So those are the things that we want to consider. So, all right, let's do it. So let's call this function, which they did not give us, a of t. And this will represent the amount of fish at any time t. So how many did we start with? And if you go through the problem, you go back and reread it, you didn't start with any, right? So your initial condition was 0, 0. So there's no fish that we started with, right? All right, plus what? Well, how can I represent the amount of fish that have entered the lake? Well, that would be the integral from the starting time to whatever time we're talking about here of E of t dt. That represents right here how many fish came in. Now, what do I have to do? Well, I have to subtract how many left. So that's the integral from 0 to t of L of t dt, right? So this is our starting or initial amount, right? This is how many entered. So how many entered. And this is how many left. It's like a three-pronged approach here. All right. So that's pretty good stuff. Now, you may notice that you can simplify this a ton and say that, all right, I don't need to do 0 plus, and then the difference of integrals is the integral of the difference. So if I integrate from 0 to t of e of t minus L of t, that's just a clean way of saying what I want to say here. So this is like the net rate. Right? When you do the incoming minus the outgoing, you get the net rate. So this will give you the net amount of fish. So this function here represents the function for the amount of fish at any time t. All right. Didn't necessarily need to do it this way, but I like doing it this way because it just seems to make a lot of sense to me. So now this is a function I want to maximize, right? You want to find when is the fish the greatest on this closed interval right here. So how do you maximize a function in calculus? You're going to be asked to do this. You have to take its derivative, get its critical points, and since we want not a relative max here, but we want an absolute max, then you're going to want to test the critical points and the endpoints in the function you're maximizing. So let's start with the derivative. So what would the derivative here be? What would a prime of t be? Well, it'd be the derivative of this integral. Now, this is kind of poor of me to not have changed this variable t to a dummy variable, since this is what makes it a function of t, not this. I should have probably did e of x minus L of x dx. I didn't. Oh, well, what are you going to do? Regardless, if I want to take the derivative of this integral, right, and I'll even write it for video flavor, d dt of the integral from 0 to t of, maybe now I'll do it, e of x minus L of x dx, right? Remember that variable is just dummy, right? When you take the derivative of the integral, they undo each other. That's the fundamental theorem of calculus, but they undo each other after that variable swap. So your derivative is just going to be e of t minus L of t, which quite honestly kind of makes sense because that's the net rate. So if you want think about it, you're trying to find the rate of which there are fish in the lake. Well, that's going to be this net rate of how much comes in minus how much goes out. Okay. And notice the starting amount doesn't mean jack, because if you were to take the derivative of whatever that number is, you're going to get 0. And that might be part of the reason why they didn't tell you. Okay. So here is our derivative right there. So you're like, okay, I got to get the critical point. So how do you get a critical point? You get a critical point by seeing where the derivative is 0 or undefined, in this case 0, right? So you'd set a prime of t equal to 0, right? And then I'll just write to find critical point or critical points. So, okay, that's just basically setting e of t minus L of t equal to 0. Now, they could not have asked you this question on your exam because you can't solve that by hand, right? So how is it that you're going to solve this? This would go in your calculator. And there's two ways you can do this. You can add the L of t to the other side. You can graph the two functions separately. You can see where they intersect. That would require you to change your x window to be x min 0, x max 8, because that's the interval I gave you. And then you're going to have to figure out what your y window would be, right? But you got 153 before for amount of fish that entered. So you can use that to kind of just figure out, what should I adjust my y max to? That's one way to do it. The other way to do it is simply put this in y1. That's probably the best way, because then you don't have to worry about your y window. You just have to worry about your x window, which they gave you, right? So put this in your calculator. So now if you did that in calculator, if you did this, and this is super rough, you're going to get something that looks like that, right? Where this is the graph of e of t minus L of t. So if you want to know where it's equal to 0, then you look right there. And that value, I believe, is t equals 6.2035 ... So that's your one critical point, okay? So you get t equals 6.2035 ... So now remember here, what's the story? Again, there's a couple of ways to do this. I personally like, appealing to the extreme value theorem, which is if you have a continuous function on a closed interval, to get the maximum, all you have to do is test the endpoints and the critical points. So you would say, all right, let's test our endpoints. So let me do a of 0 and a of 8. And then let me test my critical point, which would be a of, and maybe I'll say something like, let little c equals 6.2035, right? So A of little c. And I would test these guys. So this is testing my critical point. All right. And if you did that, A of 0, we actually knew that was 0. A of 8, you would get, let's see, if we did that, again, this would be done in a calculator. This would not be done by hand. You would get that. And if you did the critical point, you would do that. And so now biggest max, smallest min. So you're going to have the maximum amount of fish in the lake is going to occur at 6.2 hours, and it's going to be about 135 fish. All right, so this is where your absolute max would be. All right, you might be asking, how'd you do A of 8? Well, remember, you have a graphing calculator here. So to do A of 8, just look right here. Put 8 right in there. Integral from 0 to 8 of this function minus that function. Now, how could they ask this on your test? They may give you a graph where you have to actually do some sort of net signed area calculation to figure these things out. And that is certainly possible. All right, so that was a nice little question, a lot of which could not be asked in this fashion on your exam that you're going to take. All right, let's get to the last part. It says, and this is good, this is the second time you've seen this now. Hopefully you got this part right. It says, is the rate of change in the number of fish in the lake increasing or decreasing? I love this question. Is the rate of change increasing or decreasing? So they're not asking you if the amount of fish in the lake are increasing or decreasing. They're asking you, is the rate of change increasing or decreasing? So in other words, is the derivative, right? Is A prime, all right, increasing or decreasing? So what's that common concept? The function is increasing if its derivative is positive. So if I want to find out when this function is increasing, then I have to look at its derivative. So now remember, this function, based off of what we did before, was E of t minus L of t. It was that net rate. So if I want to know if that is increasing or decreasing, I have to look at the derivative of that, which should be E prime of t minus L prime of t. Now, they want to know, is it increasing or decreasing at an instant at t equals 5? So that basically means you just have to do A double prime of 5, which would be E prime of 5 minus L prime of 5, and then figure it out, right? If this is greater than 0, then you know we're increasing at that moment. And if it's less than 0, then A prime is decreasing at that moment. So if you do this, and you're like, well, how the heck would I do that? Again, maybe this may be lucky for you, right? This was a calculator question. So these functions, that could be in y1, that could be in y2. To now get the derivative at 5, how would you do it? You do n deriv of that function at 5. So this is just chuck it in your calculator. So and maybe you should do it just for kicks and giggles. If you do it, you're going to get negative 10.722. Now, I don't care that it's negative 10. I care that it's negative. I care that it's less than 0. So if A double prime is less than 0, that means that A prime is decreasing. Okay, so the rate of change in the number of fish is decreasing. Okay, so solid little concept here, asking about whether the derivative is increasing or decreasing. Okay, so great question. Obviously, it won't be asked exactly in that fashion because you will not have to have a graphing calculator, but a lot can be learned from that question. All right, hope all is well. Be good. Take care. Stay safe.